overview of my presentation. Now coming to the introduction of the proteins. We know proteins are made up from the polypeptide chains in which the basic unit is our amino acids. On the basis of various interactions, there are four levels of protein structure: primary, secondary, tertiary, and quaternary. We know that the protein is normally it is in its folded state. So there are various interactions which are responsible for the folded state: hydrogen bond, van der Waals forces, disulfide releases, hydrophobic effect, and the ion bond. Now, for the proper functioning of the protein and the enzymes, we know for the proper functioning, the enzyme should be in its folded state. But there are various phases which are present which may affect the folded state of our proteins or enzymes, which are cold, pressure, salt, and heat. So we have various kind of co-solvents which may help the protein to remain in its folded state against all these stresses. So in the earlier time, we are using organic co-solvents. But due to some drawbacks of organic co-solvents like low boiling point, high volatile nature, they are toxic and their recycling is also difficult. So we are moving for some greener solvents like ionic liquid, bases, and nanoparticles. So today I am using biomass that I have extracted from maize leaves as a green matrix for the stabilization of our protein stem bromine. So this is the graphical extract. In this, we take the maize leaf. We will going to extract the cellulose. On this, we are immobilizing our protein, and then we will check the stability of our stem protein. So these are the various material and methods that we have used. And for the sample, we have used the concentration of protein 0.5 mg per ml, and the concentration of biomass varying from 0.0 to 0.1 mg per ml. So stem bromelain. About the stem bromelain, we know that it is a cysteine protease and it has the anti-cancer properties. That's why we use them in the medical field, pharmaceuticals, and the chemical industries. Now coming to the resultant discussion. In this first, the biomass extraction and the pre-treatment. In this, firstly, we take the maize leaves. We grinded them. After the washing, we grinded them and we have the dried biomass. In this, we have used two kind of solvents. One is ionic liquid and another is imidazole. We heat them. We provide the different temperature to these two ionic liquid for the extraction of the cellulose. 80 degrees Celsius for ionic liquid and 180 degrees Celsius for imidazole. After the we will add the 0.5 gram of solution to these solvents, and after forming a completely homogeneous solution, we will take stand dish of free of acetone water mixture and stir it for 1 hour. Then we centrifuge it for 15 minutes. Then after that, we will get the solid-like material, which is carbohydrate-rich material. And for the imidazole, we add the water, then we stir it for 1 hour. Then we use the 95% ethanol solution. And in this, we will get the precipitate, same the carbohydrate-rich material. And from this carbohydrate-rich material, we will extract the cellulose by adding 3% NaOH solution. Then filter the solution. The dried part, we wash it with several times with water to improve any impurity. And after the drying, we will get our cellulose. Now the characterization, mainly our focus is there should be less intermolecular linkage between our heated cellulose as compared to the maize leaf. So these are the characterization techniques. First is TGA. In this, our regenerated cellulose from those two solvents, we can see the decomposition temperature is less as compared to maize leaf, which is showing that less intermolecular linkage between our regenerated cellulose. Then from the DSC, we can see the glass transition temperature of our regenerated cellulose is 200 and 240, but for the only the maize leaf, it is 260. So there is amorphous nature in our material, regenerated cellulose, as compared to the dried maize leaf biomass. Then from the IR, we can see the OH band around 3400 here, but we can see that there is a broadening in our maize leaves as compared to regenerative cellulose, which is showing that there is less intermolecular linkages. Somewhat our solvents are capable to break those intermolecular linkages and we can extract the cellulose easily. And from the XRD, the peak is getting more broad in case of regenerative cellulose, which is showing that there is more amorphous nature than the crystalline nature in our medium. From the same images, these last two are regenerative cellulose, and that one is our pure maize leaves. We can see the porous nature in regenerative cellulose, which is mainly responsible for the immobilization of our stem bromelain. Now, after the immobilization of stem bromelain, we need to check the stability of our stem bromelain. We use the UV visible. Here we are getting the band at 280 nanometer. After adding the biomass, we can see there is no shift in the band, which is showing that the biomass is maintaining the conformational stability of our protein. After we perform the fluorescence spectroscopy in here, we can see the quenching. There is which is showing that there is some kind of binding interaction between our biomass and our protein, which for further refinement of our how much our regenerated cellulose is combining with our stem protein, we perform the stem monomer equation. In this, we get the quenching constant higher for our ionic liquid regenerated cellulose, which is showing that there is more interaction of our ionic liquid regenerated cellulose as compared to imidazole regenerated cellulose with our protein. After to check the secondary structure stability of our stem bromelain in presence of all these biomass, we perform the series. This is a alpha plus beta protein, so we get 208, 250 nanometer and 222 nanometer. For the precise secondary structure calculation, we perform the dichroic from the dichroic we calculated the percentage secondary structure. In the presence of biomass, we can see the beta content is increasing. That is, our secondary structure is stabilizing in presence of these biomass. For the colloidal stability, we perform the DLS. In this, we can see the ionic liquid regenerative cellulose is showing more interaction, which we can see from the increasing size of hydrodynamic cells. After we perform the zeta potential, the high zeta potential is for ionic liquid regenerated cellulose. So it will going to more interact with our stem bromelain, which have the beta potential that is close to the neutral value. After for the thermal stability, we perform the thermal CD. We can see the increase of about 5 degrees Celsius in the thermal stability of stem bromelain in the presence of these biomasses. After we perform the activity of our enzyme, in this we can see the activity which is increased to 112% as compared to for the pure, it is 100%. So there is an increase in the enzyme activity of our protein. Now, after 10, we can see in the last two pictures. In the last two pictures, we can see there are more particles on our ionic liquid regenerated cellulose, which is again inconsistent with our previous result that the ionic liquid regenerated cellulose is showing more interaction as compared to imidazole. Again, in the AFM also, there is more particle density in case of ionic liquid regenerated cellulose as compared to imidazole. So, in the conclusion, we can see that there is more porous and rough surface in case of regenerated cellulose as compared to our pure maize-based solution, which provide more surface area for the immobilization of bromelain. So, as compared with if we compare two regenerated cellulose, we can see that the ionic liquid regenerated cellulose is showing more interaction with our stem bromelain, and also it is stabilizing more structurally as well as the thermal stability to our protein. At the end, I want to thank my supervisor, Professor P. Venkateshu, RCSSB team, ACT team, to provide me the opportunity to present my work. CBC for awarding me the SR of my diagnosis. Thanks.
Very nice. What was the reason for choosing healthy maize leaves?
We can use any kind of biomass because we want to exit the cellulose. We know that in the plant cell wall, we have the liquid surface. Basically the cell wall of the plants is basically made from the cell wall. So we usually use those leaves. We can use any kind of leaves.
Yeah, then what did it please? So we are done with the oral presentation. Thank you all to presenters. I thank Dr. Preetam Bolkar for chairing this session, and I hope you all enjoyed the oral presentations. Now we move to the technical sessions, and today's session brings another set of insightful talks and thought-provoking discussions. We look forward to learning from their expertise and gaining fresh perspectives on recent advancements in the field. The first session today is by Dr. Sangeeta Sharma, and this session